is not a project because it's a kind of ongoing activity, and then you can schedule a meeting every year, for instance. And if there's nothing unknown, it's not a real project, a real life project. In a real life project, you have some uncertainty. You have to be able to face it. And the bigger the project, the more complex is the setup, the more complex it will be. And here, I think that in our EU project, with API, for instance, 27 participants, funding from Euro HPCGU plus a certain number of countries, some of those not still having decided on their contribution. The level of uncertainty is certainly reaching a new level, I would say. And we certainly have to think on the best way to remain agile and efficient in the future on those projects. That's probably one thing. The other thing is, in my view, what maybe we could call the valley of death between the lab and the market. It's, wouldn't say easy, but you may have some brilliant idea, do a kind of a prototype in your lab. That's one thing. When you have to attack the market, besides that, you need some additional funding. You need to prove your idea. You need to find customers. It can take a while. And if I turn to Dynamics, I pretty sure they do understand that. And if I go to Cyprus guys, they will understand as well. I think that we collectively and Europe has to think on that and to find way to help the market grow and a kind of secure market for EU providers, and also help good ideas to go from the lab to the real market. So that's things we have probably to think for the future. You want to go ahead?
Thank you. So yeah, my answer is going to go in the same line. I think that I would classify in first technical difficulties. On those, yeah, you need the expertise and you need the experience, but I would say that that's the easy part. Even though there are big challenges, technical challenges, but those we know how to face it more or less with some uncertainty. From the years in Semidynamics, a couple of learnings that I would like to share. The first one is initially we were a very hardware-oriented company, and still we are. At some point, we realized hardware is just half of the picture, and the customers don't want to build all the software from scratch. So we had to provide a software stack because this is what the customers expect. And fair enough. I mean, NVIDIA provides a software stack, very compelling software stack. Why Semidynamics should not provide something equivalent? And the second thing is, it's not only about building great products. You can have great core, great tensor unit, great vector unit. You have to be able to sell them. And this is really difficult because you have to build the trust with the customer. If you're a big company, that's easy. If you're a startup, building the trust with the customer is really difficult. And they will ask you some questions like, do you have a prototype working on the FPGA? Okay, that's relatively easy to have. FPGAs are not that expensive. You can show them. But still, the FPGA will run at 10 megahertz, 25 megahertz. If you want performance for the real product, you have to do some extrapolations, right? And then the next question will be, do you have silicon? And if your answer is no, it's really hard to get that custom. And this is when you need the funding to have the test chip, right? And this is where, for example, the test chips from EPAC really help. Right? What else can we do to build this trust? I don't have an answer. We are exploring this right now.
I would start by disagreeing slightly on one thing. I think At least in EU pilot, we have a diverse group of partners, very many partners, but in some cases, and I cannot really speak for all of them, or maybe only a few, maybe, but in some cases they do get this funding that they use in the case of EU pilot to advance their position in the market. So, for instance, in the case of Extol, the EU pilot project provided some funding for them to develop Gen 5 PHY. This is something that is concrete that they can go to the market with. In the case of Semidynamics, and they also had a huge amount of money to get people to develop the next CPU that now they're trying to sell. Selling it is a different matter. It's really not something that, the way I look at it, it's not something that we're here for. But developing next technologies and same thing for Submer. It's another company, in the consortium. They developed the next generation of immersion pod, in part based on the funding and the ability to develop that and test it, within the context of EU pilot, right? So that said, there's obviously a gap between doing it and then selling it and so forth. So you kind of trust a little bit that these companies are using the money and funding to advance, all of them, in their own markets. In the case of Submer, they're doing extremely well because that's happening, and so for them, they have a huge amount of customers in all over the world, in the US especially, and I hear that they're even getting requests for hosting. So they're building their own data centers with immersion so that people don't have to deal with the immersion. They deal with it themselves. And so those are some examples that I can think of. Of course, research centers and academia, it's a different angle. So that's one thing. As far as difficulties, the EU Euro HPC JU funding model, where you have half and half, as you said, half of the money comes from the JU, half of the money comes from the different funding agencies in the different countries and so forth. That makes things very, very difficult, to the point that one country may pay 100%, one country may pay 10%, one country may pay 0% of their contribution, right? And so now you're trying to figure out how to make that work, because for every euro that you spend, you have to justify the other side as well in order to get that euro from there. So you have to put it out of your own pocket as well. So that caused a huge amount of issues. Overall, in my view, I think in Europe, we have like this huge hole that it's slowly being, well, I wouldn't even say covered because it's not quite there. It's EDA. EDA for building tools, these tools for building chips and designing chips, especially now with the more complex things like chiplets. That's just expensive, really, really expensive for even doing the smallest things, verification, for tools and stacks for protocols like PCIe or CXL or things like that. And so we're not really even on that conversation where some of these standards meetings are taking place. So that's another thing. From the EU pilot side, and my experience is also somewhat difficult to get really coordinating 19 partners is hard, and making sure that everything more or less matches and things kind of move forward, when in reality, the initial documentation may have forgotten some areas. Now you get into a situation of what do you do? this was forgotten. Who's going to step up to do the job? And then so you have, some organizations that are more willing to do it, some organizations that are less willing to do it. And so there's a little bit of politics and jockeying around, all these things. So those are another difficulty from my point of view.
Right. Matteo, from your side, would you like to add your own perspective? I know you have had extensive industrial experience as well, so perhaps you have your own unique perspective here. Yeah, we do see you. Yeah, thank you.
Yes, thank you. Thank you for all your contribution. I attended the whole workshop today. Yesterday, of course, I was not in, but it was very interesting. You covered most of the hot topic, and also I think that the co-design part is at the moment is extremely relevant in the future data scale system, HPC system, and beyond the HPC also for artificial intelligence, and you covered all the aspects. About your questions, I will stress that I'm here not to talk on behalf of EuroHPC-JU or the European Union in general, so this is just my humble, very humble opinion about the situation. I as an European citizen, an European former scientist, I would say, so I think that the European Union spent a lot of money in order to create an ecosystem that I do hope that will grow beyond the HPC technologies. And so I think that all the various technologies that also today you showed us will provide technological knowledge that could be exploited beyond the HPC. For the future, I will distinguish two things. One thing is the general purpose processing that I do hope that the ecosystem that Europe has created could exploit what we did so far. But for the HPC, the next steps of the HPC, that is the data scale perspective, I think that maybe the traditional HPC made of components that we assemble, we glue together every time will at some stage end because mainly of the power consumption. And no, I guess that all of you are aware that we are expecting hundreds of megawatts, and also some estimation are showing gigawatts of power consumption in the next steps of the HPC, so the data scale. And I wonder if it is really sustainable, this kind of ecosystem. So maybe for the HPC, the traditional way of building chips and gluing it together and building and adding the software will end, and maybe we should reconsider the way we design the HPC. I noticed that some companies in the private sector are focusing the attention on the mission, so-called mission-specific HPC, that may be a solution in order to address the data scale. So also the chip, the whole ecosystem should change and should consider new kind of co-design also. I mean, the co-design should return a hardware and software endeavor that are glued together in order to that are not glued, they are co-designed together and in a way that is a real co-design that can exploit all the efficiency that we can have in this system, and at the same time could save power supply and power consumption and so on. I mean, everything that is at the moment is not so efficient and is growing, highly growing from one generation of HPC to the next generation of HPC. And there is also the problem of the cooling that also today was addressed. So maybe thinking the system, the machine, the HPC in a different way, exploiting, for instance, the interconnection between the accelerators in a different way. So approaching the co-design in a real co-design way maybe could be considered for the next generation of HPC. Thank you very much.
Thank you, Matteo. Shall we do a second round on these type of ideas? For example, starting from the last speaker, he pointed out the possibility that we can do extreme specialization. Matteo, I'm probably oversimplifying of what you said. Machines that are co-designed, hardware and software, probably mission-oriented, under the power delivery constraints that are very pressing and will get even more pressing. Jose Maria brought up the concept that we started as hardware only, now we are hardware plus software, and probably the trend is that both sides of the house need to grow at an extreme pace. The question that we need to be able to do demonstrations of very advanced functionality, although we are not capable of delivering at the time that any customer or situation demands it. So projections, test chips, performance analysis, all such things seem to be classical questions, but now I think they are interleaved in a new and more, shall we say, demanding manner. Is there something that any of you would like to add to that, or perhaps disentangle the issues? I entangled them probably more than you had in mind. Carlos brought up the coordination aspect, likewise, 19 partners, 27 partners, whatever might this mean. If we add the external suppliers and the special relations that we have, I think the numbers are effectively higher than that. Managing vendor relations, tools. Can you help disentangle, to some extent, all these difficult questions? Please.
Could I try to start? So I will not speak here on behalf of the project or my company. So it's a kind of spontaneous thoughts. I think co-design is something I do believe it's something important, and we had the chance within a PI project to have a space for co-design, and we have also some discussion with other projects. And today workshop is a good example, and I think we have to take care in the future to have space for future co-design. So that's important. So it may be part of CSR action, it may be part of future project, but and by nature, co-design should join people from different horizons, different angles, to share, I would say, efficiently. And that's something to keep for sure, and to maybe to promote for the future. And beside, maybe we could have more delivery-oriented project targeting a specific purpose, and this may rejoin some of Matteo's thought, and maybe with a more focused group within the project. Then, so maybe we should think on articulating different kind of projects as on another level we are articulating research-oriented things with more industry-oriented action. So this is something we have to keep in mind, and certainly think for the future. Besides, to be optimistic, we can see a growing awareness on sovereignty concern, also on industrial concern in Europe, and we can see the budget of project increasing quite seriously if we compare to what was done in the past. So Mont Blanc project, it was about 8 million funding, so it was not so much for a 3-year project. Now we are at a much higher level. We can speak here for API, but also for UPEX, UPilot, Net4Exa or their project. So we can see several projects emerging with a bigger budget. This is certainly not ideal if we compare to the competition we may have in China, in the US, etc. But it's a big step forward. So we can take that as a good point, certainly, and think how to go further for the future to be able to sustain this effort. But I think this has to be said, and it's really a positive thing, together with the awareness I was mentioning before.
Carlos, would you like to say a few words, and José María?
So I want to maybe mention a couple of things. One thing related to the last talks, the last 2 talks that we had. I mean, I know from my own experience, so I was architect for power management at a couple of companies in Silicon Valley, and even 20 years ago, we knew that essentially at that time, the electronics were built with a specific lifetime. And the trend had been and continued to be all these years to go higher frequencies, higher performance, and also deeper and deeper nodes. And so what in the end you have is you end up having to cut that lifetime. So essentially, it used to be that you would get that component and it would have a warranty of 10 years now. And so in the specific case that I was involved with CPUs, we, in terms of power management, we could go up to a certain frequency. And that frequency was determined through a number of things that I'm not going to go in here, but you basically would bin the parts, right? And, you also had internal information about, structures, ring oscillators and whatnot. But at some point, we leveraged some studies that basically said, well, given this envelope of operation at this frequency and with this temperature, you can go above this frequency if the part can handle it for a certain period of time, provided that you don't go over that temperature limit and that frequency limit for too long. So eventually we kind of pioneer it. And so it was basically what later on Intel called it turbo mode. So the turbo mode is basically that if you go too far into those states, you essentially, it's like flying a plane and you're flying it too fast, but you can only fly it, if you fly too long at a specific angles or whatever, it may overheat, and then you start losing pieces of the wing. So here you get depletion, and you get basically you get less life on the electronics. So that's not going to get any better. So there's no question about that. We're pushing the envelope on there. So unless something happens, that's not going to get any better. So that's one comment based on what you guys are doing. So I think that's important. So that was a comment regarding that. And I don't know if you have any more comments in general.
Yeah,
Or-
I would like to. Yeah, thank you. I would like to elaborate a bit on the co-design idea, whether we should co-design the software and the hardware together. And I have mixed feelings about this. And the reason is machine learning is a very fast moving target. And it's a mistake to over-specialize or overfit for existing solutions. I can tell for experience that I got tired of accelerators, pure accelerators in the past life, that were not as programmable as what we have in semidynamics. And the accelerator was outdated before we finished the tapeout because they invent residual connections. They invent attention models, right? This is continuously evolving. It is true that the more you specialize, typically the more efficient or energy efficient can be your solution. You can get better PPA, but we prefer to not over-specialize that much, even though we know we're leaving some PPA on the table, to be more future-proof and to be able to adapt to future changes in AI algorithms. And we are seeing this now. Remember, we implemented Int4 and Int8 support because machine learning was using quantization, and this was very popular. At some point, they say, no, FP8 and FP4, please. We implemented that. Okay, it's great, but now what we want is microscaling with the shared exponents. Okay, this is just an example that machine learning is a very fast-moving target, and it's really hard to find the good point in the design space between programmability and the
scope processors, right? So you basically figure out at one point, it's like, wait, we need to do this. And then you can do it in the software, and then, chaos happens for a while. Then people stabilize on something and they realize, okay, this is useful to do. Let's do it this way. What happens next? It goes into the hardware. Much more efficient, much more capable, much more everything. Same thing with graphics. People were doing graphics the old-fashioned way with software and whatnot. Once there's an API and a consensus as to what's to do, you go from one side and then you go to the other. The hardware absorbs it. Right now, we are, in a way, accelerating a little bit too much in terms of the hardware building for AI, because really that's what's needed. But eventually, it might converge. You might see something like what DeepSeek made, right? They made a huge reduction on the amount of resources that are needed, and then people will do that, right? And so some of that will just go into more efficient hardware to do specific things. So if you look at it, I mean, for a while, for gaming, there were physics accelerators. Anybody remember those? They worked out, there was a lot of physics simulation in the software, and then they go into the hardware. But then people figure out, okay, we can still do the same thing in GPUs, maybe more efficiently. So my point of view is that we have these cycles of like understanding things, new things happen. We really just understand them, really. And then once there's a general consensus or some view of the API or whatever, then it just goes, it gets absorbed into the hardware much more efficiently. And there's a clear API as to what, and then that's part of the reason you have standards and APIs and how people evolve as to now we want to do share memory with caches and with CXL with remote memories or whatnot, right? So people start to do, different things first on software, and then eventually, they go into more efficient ways. And that's part of the co-design. Part of the co-design is really understanding what's to do best. That's my point of view.
Matteo, would you like to say a few more words about that? For example, about the danger of over-specialization, about this concept of co-design being based on deeper understanding over time, and this pendulum of changes and mainstream and back? Or if you have a strong view about these positions, or if you see complementarity?
What I can see from my privilege, I would say, point of view, I see that the computational, the intensive computational tasks are moving from the CPU to the accelerators. This is a general trend since a long time ago. So now the computational power is mainly based on the accelerators, and there are several kinds, as you know better than me, several kinds of accelerators specialized, very specialized for a specific application, for a specific part of the code. So, as I said before, I think that the so-called the general purpose HPC is ending, is reaching an end at some stage, because I think that if everything is done in the accelerator, so the next stage of the HPC will be mainly based on the accelerator, and the accelerator should be specialized into the specific applications that we are going to run. So if there is, you know better than me, if there is an artificial intelligence or machine learning application, it cannot be run in a generic CPU, in a generic, if you want, of course, to run it very efficiently. So it is not an HPC that could be, in my humble opinion, general purpose in the future. So we should target, as I said before, a specific mission oriented HPC. So if we needed to run a code, specific code, we needed to tailor the accelerator to that specific code. And also the whole system should grow on this kind of architecture. So also the interconnection should not pass through the CPU. I mean, it is just a waste of time. So we needed to focus on interconnections that are close connected with the accelerator and also to the data set. Now we have very large data sets that the computational engine, the computational elements should elaborate. So also the access to the data must be very quick in the future, I guess, if we wanted to be efficient, if we wanted to run efficient code. But as I said, tailored to the specific application or the specific set of applications, if you want to be more generic, I would say. So it's these two aspects should be, in my humble opinion, considering the next generation of the chips that we are going to build. So it is not just one chip that is the solution for everything or one accelerator, but a set of accelerators that should be integrated, well integrated in the system. So it should be the co-design between the specific application and the accelerators, the various accelerators that we needed to integrate together, and they cannot be glued together. I mean, they need to be designed together. So this is the co-design, the real co-design, in order to be also energy efficient. I mean, now, of course, we have in the modern CPUs all the software, I mean, the application in order to tailor also the power supply, so we can move the power efficiency from one component to another component, or to one part of the chip to another part of the chip. But this optimization, I would say, of the power supply should be improved in the next generation of CPU and GPU and accelerators in general, because the power efficiency is going to be extremely important, because I think, this is my humble opinion, that the power supply needed in order to feed the next generation of the HPC is so huge that I'm not really sure that we can sustain this kind of general purpose HPC. This is my contribution. Thank you.
Right, Matteo. So I understand that you see this extreme, shall we say, challenge around power, energy, actually, and you see that we need to consider systems that can take advantage of connectivity. Perhaps if you could elaborate, if you consider both cluster-wide or site-wide connectivity, but probably also technologies like interposers, chiplets. Is this part of your technical vision? You mentioned connectivity, and perhaps you could clarify a bit more.
Yes, I think
various ranges, right?
I think that following the technological trends are not the best for the European Union. I mean, of course, it is. I mean, the technology, following the technology is in some cases. I mean, it's trivial, I would say, because you just move from 10 nanometers to 7 nanometers and to 5 nanometers, and you change your libraries and you design your chips. You need to verify your design, so it takes a lot of time and then a lot of effort, a lot of people, designers involved, and so on. But I'm not really sure that Europe is the best on this kind of effort, especially because the competitors, and you know better than me, I mean, around the world are very strong, very very efficient in that. So is maybe for the next generation of the HPC that is going to involve millions or maybe billions of processing elements working all together in order to achieve the data scale target. Maybe the fact that we run at the faster clock or we involve 1 nanometer technology is not so relevant, and we should maybe consider the close interconnection between the processing elements that are not the GPU anymore, as far as I can see. I mean, please correct me if I'm wrong. I see that the processing power is moving from the CPU to the accelerator. This is the general trend. So it's if that is a situation, we need to consider new kind of interconnection between the accelerators. I think that the low latency, of course, the low, I mean, you know better than me all these aspects. And maybe we should not rely on system calls of that in order to achieve a communication. So it's a new kind of HPC that maybe we needed to think. Maybe the chiplet could be the solution. As I said, I'm not really sure that we are the best on that. And following the technological trends means that you need to compete with the top leaders in the world, and these are trillions dollars companies. So they have a huge amount of money, and it could be difficult. Just an observation as an European citizen, and maybe we needed to think something different in order to exploit the solution. I mean, to adapt, since this is a code design workshop, to co-design in a very well done way our supercomputers in order to match the needs of the applications. So I think, as I said, stressed several times, an application-oriented architecture for the future, where the machine and the software are tailored together, co-designed together, really co-designed together, in order to achieve the best performance from the computational power and also from the power consumption point of view. As I said, the two aspects are, in my humble opinion, they are going to be addressed together in the future, needs to be addressed together in the future. And the interconnection, of course, could be done by using the new technologies that we are new. They are not so new. I mean, we started a long time ago in assembling chips together, so it is not really new. So we could also think that to integrate in the same chiplet, for instance, or in different chips glued together with the interposer and so on, the interconnection and the accelerators, and then implement it in a system. But as I said, the co-design should be a real co-design. So we need to design the two things together in order to match the hardware and the software in a very efficient way. This is my humble opinion, of course.
Thank you, Matteo. Perhaps Etienne would like to add to his position.
Yes, a couple of brief observations from my side. I do agree really on the fact that we have to open the window or the door to new ideas and search new ways. That's for clear. Besides, we have kind of legacy, and we also have system, and we have to think on the evolution of the existing application. So we have to find the right balance, or maybe pendula, but between those two aspects. I remember a discussion I had with people working on aircraft modeling things, and they were telling me that they were working on an application to be used 15 years away because of the time due to realize the application and then to test it seriously, because when it's about aircraft, life may be at stake. So it's in some case, we may have some applications that may have very long life cycle. And beside, as mentioned before, we have some new applications with very short or new techniques with very short life cycle. So we have to find a way to combine that. And beside, for sure, power efficiency is something critical. I think we are rather good in Europe. So if we, it has been mentioned today, if we look at the best system in Green 500, they are in Europe, and Europe is, I think, most of the place in the top 10 in Green 500. So it's right now a concern in Europe, and we are good. So, but for sure, we have to go on to sustain, to push it further. But here we have some element already in our baskets, I would say.
I would like to say that I also advocate for the accelerators. Actually, we are selling accelerators, so of course, I'm supporting this. But for me, the question is for AI, which is the degree of programmability for your accelerator. Because if it's too rigid, you are dead in 2 years because the algorithms will change. If it's too programmable, you are losing a lot of efficiency. So in this regard, for me, the right thing to do is identify what are the fundamental computations that your application is doing. Because some people believe that accelerating is, no, you provide your application, you see what are the bottlenecks, the main C functions, and then you build hardware for this. No, if you do this, probably the tasks that you are offloading are too coarse-grained and it's too rigid. So it's not an easy game, and it's about finding, okay, if the task that you are accelerating is too coarse grain. Probably it's not going to be generic. It's going to be overfitted for a given problem, and it will not be relevant over time. Of course, if you make it too fine grain, offloading to an accelerator has a cost. So if it's too fine grain, the cost of offloading to the accelerator will kill the performance benefits. And I can put some examples. Some DNN accelerators have dedicated hardware for specific activation functions. That's okay, but machine learning practitioners like to constantly invent new activation functions. Today is softmax, but in 1 year is a different function, and in 2 years is yet a different function. So for example, what we did was we identified that the vast majority of activation functions use exponentials. So maybe it's a better idea to have dedicated hardware for exponentials because we know it's more generic, granularity is big enough, and this is going to be used by many different types of AI applications. So for me, the question is, what is the degree of programmability? And it's not easy to find the correct degree, and it's not an easy task to identify what are the fundamental computations that are generic enough so they will be relevant in the future.
Agreed. Just to take a very simple example, Intel with this 512 vector length was quite rigid, and with ARM and now with RISC-V, we really go beyond. And this is a flexibility that is a real benefit. So we should not lose ways of flexibility.
I don't know. I go back to the origins. Why was MMX invented? Why was all this invented? Because people needed to play DVDs. And so they need acceleration for video processing. Eventually, once enough of the video processing was understood, that stuff was left, but then, hardware accelerators for video, MPEG acceleration and whatnot were put into the hardware much more efficient. And then people are constantly trying, new ways to do things more efficiently, sometimes in the software. But to me, it's like a little, it's an exercise that we have to go through to kind of, in a way, collective learning and agreeing in some ways as to what is the most beneficial way of doing a certain thing.
It's a part of competitive process.
It is part of a competitive process.
Okay. Perhaps we can take a couple of questions from the room. I think you have added a lot of fuel to the fire, and I appreciate that a lot. So who would like to start from the low part?
Thanks for your discussions. There is on top of programmability, there is another concern is the curve of learning. We should have some technology that is easy enough for the new generation to take it over, to program it, to use it. And I don't know if this is also a matter of discussion in this co-design workshop.
Of people?
Yeah, you will design a new hardware with, a way to program it, because it has to be programmable to not be obsolete in 2 years. You need a language that will be efficiently translated to what will execute new architecture, and this language needs also to be efficiently, compiled so that it efficiently uses the architecture, but easy enough to learn for the new people to use the language and the technology.
Next generations think differently by nature in many ways because they have things in a different way. I heard an anecdote recently about the mindset, a little bit of the Gen Z of the newer generations. Somebody needed, I guess my age, was telling, they needed 50 blank pieces of paper for doing something, and they asked an assistant, it was a Gen Z or whatever. And then when they brought the 50 pieces of paper, they noticed it was warm, the paper. It's like, what do you do? It's like, well, instead of counting them, I just press 50 and then did blank photocopies. So it's a different way of thinking that you normally would not think. So next generations will probably take advantage of some things that we may not see today. That probably does not answer your question very much, but
Jose Maria, you mentioned a lot programmability.
Yeah, of course.
I guess, and you mentioned during your talk that you are considering higher level languages, including C++, etc. Perhaps you can add to the question.
Of course. Yeah. I would like to clarify. As you said, one thing is it programmable in the sense is it flexible to do different kinds of computations? And then there is your question, is how easy is it for a human to actually extract some performance out of this architecture? Especially scientists, right? Or not scientists from other disciplines, not computer scientists, right? You want a chip that all the programmers can extract some performance from that. You don't want to build a chip only for HPC experts. And I shouldn't be saying this, but the bad news, it's going to be hard to program. And there is no way to go around it. The new systems are multi-core. You have to think in parallel. That is also harder than thinking sequentially. And it's highly heterogeneous. You have vector, you have tensor, you have a sea of accelerators. So it's going to be difficult to program. But for me, it's a matter of educating people. And 15 years ago, there was the mantra that GPUs were really hard to program, that nobody could program GPUs, and that they were really difficult, right? Because the programming model was different to CPUs. That was what people was used to. But I believe that some companies did a very good job going to the universities, working with the professors, saying, hey, teach CUDA to your students, I will give you GPUs. And I believe we should do the same. I mean, going to the university, we need universities to educate future programmers that will be programming whatever new chips we develop in these projects. And we have to do the same. It works really well. We have to go to university, says you have these chips from EPI. Please teach your students, teach RISC-V, teach your students to program these processors.
Matteo, would you like to add to this question? And then I go to another question there. Programmability, learning curve to get going with the advanced technologies.
Yes, as I said, I mean,
With your co-design view that you presented, I
yes,
guess.
I think that the exploiting the new accelerators that we are going to have, and you today showed a lot of different accelerators in your presentation, your various contributions, will be very challenging because they are different, and also I think that we should consider the reconfigurability of the hardware. I mean, these are key elements also. I mean, we should adapt if we wanted to address a sort of a general purpose approach to the applications. The hardware should be not just programmable, but also reconfigurable, depending on the kind of application that I'm going to run. The same for the interconnection, and the same for the data access. I mean, the data access, sometimes I notice that in my my life. I mean, I'm dealing with all these projects, so I'm privileged from that point of view, because I see also different applications running in the various HPC ecosystem. Sometimes the data set is highly heterogeneous. So in some part of the application, the data set is just kilobytes. And in other cases, there are a huge amount of data to be considered, and it is very difficult for the system to elaborate to all this huge amount of data. So it's also this aspect. So it is the programmability, taking into account also the data set that I have. So program to sum up, having able to program the next generation of the accelerators in a very efficient way will be very challenging, in my humble opinion, in order to exploit, as I said, the whole computational power that we have in hardware. And as I said, we needed to tune the hardware with the application, the software as well. So it is something that is going to be very, very challenging, in my humble opinion. Thank you.
Yes, I do agree, and we will have to face a diversity of situations that is certainly increasing and will become quite huge. And with, as you said, some characteristic, data patterns, etc., or volumes that can be quite different. And so that's a side remark. That was also to try to find a global model. It was one of the initial reasons we did set this common platform ID, so which has its limit. But by the way, we have to find kind of standard, I would say, at different level, at software level, some common programmation model, also at hardware level. And RISC-V ISA is a good example. We have to find the right standards where we can deploy our imagination to improve the things. But I think co-design is about defining some common grounds, and these are examples. And beside, we have to imagine and improve the solution and push the models further.
So speaking about programmability, in the end, the software developers only see a few libraries. They don't know what's happening underneath, under the hood, and they don't really care. And we can try to go closer, now reach the programmers, or we can hope that programmers will try to optimize their things. But the trend I'm seeing is that programmers these days don't care about efficiency. Especially in HPC. I mean, I have some colleagues in the next building here from the astrophysics department, and they're running this huge project with like lots of data. They're trying to create a 3D map of the universe. They need like gigabytes of data, hundreds of gigabytes of data for every run. And they're doing the whole very computational intensive, and they're doing it in Python, okay? And I'm trying to, help them profile their code. And the answer is, okay, it will take a lot of time to profile my code. It will take a lot of time to parallelize it. It's somebody's PhD. Until then, I'll just pay a few, like, I don't know, hundreds of thousands of dollars and buy another NVIDIA rack, and problem solved. And nobody cares about efficiency. So we're talking about code design, but what I see is the software people are running away from hardware. They're just going higher level, using higher level languages. They don't try to even, understand what's happening beneath and optimize. Like what, for example, code the libraries, Carlos, you mentioned. I remember FFmpeg, they tried assembly optimizations to make things right. That's not what we see now. So how do we approach code design where software is running away and hardware is also trying to be simpler in order to be more efficient? So where would we meet?
I would say that's a kind of Sisyphus challenge, and every time we try to redo it or to find the sweet spot. And I would refer also to Filippo's talk this morning, saying, okay, we have several levels of optimization that are doable. The easy one is to let the compiler do, and of course the harder way is to go at assembly level to optimize the loop, and in between we have to find the right way according to each situation. But yeah, I think it's a continuous challenge.
Okay, any further reaction to that?
Just a quick one. People care about going fast. Programmers care about doing things fast. And you're right, they don't necessarily care about efficiency. But the people who have to pay for those systems care about efficiency because they have to pay for power too. And so, when the bill starts to add up, then it becomes an issue, which then further the administrative side of it eventually comes back. But yeah, you're right. I mean, who remembers when MapReduce came along, right? People were like, "Oh my God, now you have PyTorch and you have Jupyter networks and all these things that make things like that, and you're doing a bazillion things with one thing, with libraries, exactly, right?" And then once people start to realize that a bunch of these things are just the common thing, we're a little bit early on the AI world, and eventually that will be by the sheer amount of numbers, that will be made more efficient. But you're right. I mean, it's different. The programmers themselves don't necessarily care about efficiency.
So is there someone else that would like to ask a question to our panelists as we go into the wrap-up phase? Probably a lot of food for thought. I would like to thank the people that took the time to be on the panel, particularly Matteo. I hope we didn't inconvenience you too much by being a bit late in the program. We appreciate
No
it.
problem.
And
Thank you.
We'll be over tomorrow as speaker and panelists again. So again, big round of applause for our esteemed panelists. And that's a wrap. We have a couple of practical things to say about the rest of the day, but
and before just excuse me, Mandaris, I think it's a good time to remember we have another panel tomorrow, which will be an exercise of co-design, because here we will meet the expectation of the COEs together with what the technology provider may propose. So I think it can be interesting also.